So once again, I want to say a big welcome to all of you. Regression establishes causality. And the essence of regression is to minimize the error sum of squares, find the beta coefficient, which tells you by how much any independent variable influences the dependent variable. And then based on that, you can make predictions. So when there's a change in the dependent variable, when there's a change in the regressor, the independent variable, how is that going to affect the regressant? How is that going to affect the dependent variable? That is what the beta parameters, the coefficients, actually tell you. So there have been so many ways of finding the beta. There are so many mathematical ways. The original one is the OLS. Maximum likelihood estimation is another means of finding the beta. The generalized least squares, the feasible generalized least squares, or the weighted least squares. All of these are means of finding this beta parameter. Now the question is, how do you find it? You see, if there are a lot of independent variables, and usually there are, then the way to finding the beta is to use matrix. It's an easy way. So if you look at this equation here, this is a clear indication of a regression model. That is a simple indication of what a regression model is. Now, if you look at it carefully, and I want to believe that you can see it. Right? Okay. If you look at it carefully, you will notice something here. You will notice that the y is the dependent variable, this y. And then the x here is the independent variable. This beta is the beta parameter, the estimator that we want to actually find. And of course, the error term is this one here. Now, we can apply some manipulations to this. We can apply x prime x throughout. Now, x prime x is just the inverse of x. And so when you have an x and you turn it the other way around, you get an s prime s. If we apply s prime s through the equation, we haven't changed anything in the equation. And that is what this one is. Based on that, we can find this beta parameter. One way we can find is clearly, see from here, we can divide this bottom side by x prime x, and then divide this one too by x prime x, divide this one too by x prime s. And then we can take the expected value. Now, if you take the expected value of the error term, one of the assumptions of regression says that expected value of the error term is 0. So the whole of this one becomes 0. This one, the expected value will be itself. This one, the expected value will be itself. The expected value of the beta is beta cap. The expected value of this beta is beta cap. And again, this is provable. Okay, the expected value of this beta is equal to beta cap. That is estimated. It's provable in several books. Therefore, we are left with these matrices, and these matrices, you can't take the expected value because they are themselves. Therefore, on this section, the x prime x will cancel the x prime x, and then we'll be left with the beta. Then on this section, you have x prime y over x prime x. And x prime y over x prime x, if it is a ratio, and so I can move the denominator upward so that you are getting x prime y, take this one up, then it becomes x prime x to the power -1, because you just moved it from the denominator to the numerator by virtue of transpose. That is it, and that is what you have down here. Therefore, we can say that the beta cap is equal to the x prime x -1 x prime y. This is what is known as the OLS beta. That is a basic standard econometric way of determining the beta. And this is coming from a data set that looks like this. So the original data set, this one is in the matrix form, okay, in a matrix form. But in an actual values form, we get it in this form. This is the beta cap. Now, anytime you have a data set, there are two things that you really want from the data set. One, you want to know the average. And then two, you want to know the dispersion from the average. Any data set, basically, you want to know the average can include the mean, the median, the mode, and all of that. The dispersion from the average can be the standard deviation, the variance, the range, the ketosis, the skewness, and all of those mumbo jumps. Now, regression is an average measure. If you can remember the data set, regression is an average measure. And so when you might decide, for example, to collect all of these, okay, and I have a regression, and I have a data set, a data set, a data set, a data set, a data set. What a regression would do, let's say this is X and this is Y. What a regression would do is to just throw a line through this data set. And it throws a line like that. That line is a line of best fit. That line is indicative of the average. And then you can find deviation from the line, which is the dispersion, deviation from the line, which is the error, deviation from the line, which is the dispersion, deviation from the line, which is the error. And then when you now take the average of this deviation from the line, we have something like the variance or the standard deviation. So regression is basically trying to, determine the average as well as the dispersion, the deviation from the average. That's interesting. And you know why that is so interesting? That is interesting because now we have found a beta parameter. The beta parameter is this, which is representing the sort of average impact of each variable, each independent variable or the dependent variable. Now we need to find the dispersion, the standard deviation, the variance, the movement away from the center. How do you do that? Now, what we are going to do now is we are going to now go to how to generate that. And that is what we call the variance covariance matrix. You see, the variance covariance matrix has a lot of useful things. I'll tell you about it later. But how do you prove that this variance of beta cap is equal to this homoscedastic variance? What you see here is the variance covariance matrix, which tells you a lot of things. And I will tell you the importance of the lot of things. So how do you prove that the variance of beta cap is equal to this, is equal to this, is equal to the sigma square x prime x to the power -1? Now remember, this x prime x to the power -1 is just a matrix of rows and columns, a matrix of rows and columns. Okay, so you have a column of dependent variable, a column of several independent variables in the data set in an Excel, that's it. Now what is key is this one here. That is what we call the homoscedastic error. What is that? What is that? So before I tell you what that is, we need to prove it that the variance of this value here is equal to the final value here. We're going to prove that called error demonstration. We're going to do that. But first, you got to understand that the expected value of beta cap minus beta prime and beta cap minus beta without prime is also equal to that. So first, you need to know this. What is that? It is expected value of beta. Okay, what is this? This is a true beta value, the true coefficient. But you see, the true coefficient is never known in practice. You don't really know the exact impact, the exact true impact of an independent variable on a dependent variable. That's why we estimate it. And when you estimate it, you put a cap on it. What do you mean by you estimate it? You mean you estimate it by taking the data and then picking it from the data and then, letting the data, fitting the data onto this, letting the data speak to you. So this beta cap is what we have estimated here. This is a beta cap. which is actually the variance covariance matrix, sorry, which is actually the x prime x to the power negative 1. That is the, the transpose of the x prime x and the x prime y. And again, if you're a little bit lost about what is x and x prime, x is a whole thing. So I can say that this one can be x1, x2, x3, and then it contains data 1, 2, 4, 5, 6, 9, 2, 10, 11. And all of this is a matrix, and I can represent it by x. That's what we mean by the x. And then when I convert the rows into columns, then I get an x prime. And so the way this one comes down, 1, 2, 4, 5, 6, 9, 2, 10, let me say 8 here. You can turn it away and make it 1, 5, sorry, okay, 1, 5, 2, okay, and then 2, 6, 10, and then 4, 9, 8. So this becomes the x prime x, the x prime. The rows become the columns. Okay, so keep that in mind. And while that is in your head, let's go back here. So keep that the beta cap is equal to x prime x negative 1 x prime 1. Well, what I can do is I can replace this y here, this y alone. I know that this y alone is equal to this. If you can remember, y is equal to x beta plus the epsilon. So wherever I see y, okay, I'm just going to put, wherever I see this y, I'm going to put this one there. And y is here, so I'll replace all of that with this. That's it. Nothing has changed so far. I still have my beta cap there. And now there's one more thing I can do. I can decide at this stage to expand, because you watch it carefully, you can see that this outer layer information is multiplying here, what is inside. So it's like you have A outside, and then you have B plus C. And so you multiply AB, and then you have BC. That's what you are expanding. Now, how do you expand? It's simple. Take the whole of this, multiply by that, which gives you what? It gives you that beautiful, beautiful, beautiful information here. This whole thing. Because it's the whole of that multiplying the x beta. And then the whole of that again multiplying the x, the whole of that again multiplying the error term. And that's what you see in the second layer. The whole of this multiplying the error term. And so what is this value? Well, you can see that this value will give you 1. Why? Because if you have a to the power negative 1 times a standing alone is also to the power positive 1. And so that gives you a to the power negative 1 plus positive 1, which is 0. Any number raised to the power 0 is 1. Therefore, the whole of this here is 1. And that is why we are left with only beta, which is what it is. And then we are left with the last part. The last part, we don't touch it for now. We keep it here. I hope you're following. At this stage, we can come back to this, which says that we should take the expected value of the whole of this. Now, first, we need to take the expected value of the beta cap. What is the beta cap? The beta cap is what is here, this blue thing. Okay, what is the beta cap? What is the beta cap? What is the beta cap? This is the beta cap. Okay. When you go here, the whole of this is now the beta cap. Now, I want to take the expected value of this beta cap, which is that one here. So that means that I'll take the expected value of this beta, yeah. Then I'll take the expected value of the whole of this. Now remember, this is the error term. The expected value of the error term is 0. So multiplying the whole of this becomes 0. That is why we are left with eventually beta cap. Therefore, the expected value of beta cap is beta here. Now, we know from now that expected value of beta cap is what? Beta. Keep that in mind. Keep that in mind. Now let's go and do a proof. Let's go and do that beautiful proof. It's very simple if you have understood all of this. What is a proof? We can now prove the variance covariance matrix. So the question now here is this. What is the variance of the beta cap? Now remember, we know that the expected value of beta cap is beta. We know that. But what is the variance? Now, by the way, when we say the expected value of beta cap is beta, the expected value of any number is actually the average of the number. It's like the mean. So the expected value of a series of numbers, 298, is the mean of them, is the average of them. Of course, you got to be specific of what kind of mean. So the same way, that is the center. Now we talk about deviation from the center, which is the variance. So what is the variance of beta cap? The variance of beta cap is given by the expected value twice. It's expected value twice. So in other words, the variance of beta cap is actually expected value of beta cap prime, and then expected, and then that of the beta cap. That's it. This is a variance. This is a variance. Now remember, one has a prime and the other does not have a prime. This one here has a prime, and this one does not have a prime. They are both beta cap, beta cap, beta cap, beta cap. So we know the value of this beta cap. What is that? Now remember, let's go back here. The value, just find out what this beta cap is. This is a beta cap. Watch it here. Beta cap. This beta cap here. This beta cap here. This one here. This beta cap is equal to the whole of this blue information. This blue information. This blue information. Therefore, the beta cap is the whole of this blue information. Therefore, the beta cap is the whole of this blue information. So we got to take this beta cap, which is this whole blue information, and dump it into this one with a prime. Then we do the same thing, dump it here without a prime. Let's go down. So we come here, okay? Here. We dump it here with a prime. So the whole of it is dumped into this beta cap with a prime. That's a prime. And then the other one, dump here without a prime. We are done. At this stage, it's a matter of simple two principles and then manipulation. If you look at it, the whole of this with a prime is multiplying the whole of that without a prime. Remember, they were beta caps, but here they are beta, 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 beta. So we can cancel some things. Can you see that? For example, you can see that this minus beta has a plus beta here. Gone. Let's keep the rest in the prime. This plus beta here is going to cancel the minus beta. It's like beta minus beta, giving 0. So what is left are the x primes and then the epsilon. The x primes and the epsilon. Oh, beautiful. Therefore, the variance of the beta cap is given by these ones and the epsilon, which has a prime. It has an inverse. And then you have this one without a prime. Simple. At this stage, we can multiply these two. But remember, one of them has got a prime with this red prime. The other doesn't have. Oh, the cancellation is beautiful. But before that, remember that the transpose of a number, sorry, the transpose of a number is the number. So what is the transpose of x? Transpose of x is x prime prime. That's the transpose of x prime. And so because x prime is the rows converted to columns, and now the columns which has been converted is now converted back to rows, so you get an x. Take this, keep this in mind. You see, with this in mind, then we can easily manipulate this. Because watch it, this red prime is here. Multiplying this against x prime prime, which gives you x. This one doesn't have x prime, so it becomes x prime when you multiply by the red. This one has x prime already, so it becomes x prime prime, which is x. Then all of this, so watch this. And again, it might look like I'm speaking in Hebrew. So this first one is going to be x prime prime, which is x. I don't want to write it. This second one here, okay, it is going to have x prime, okay, and both of them are having to the power -1. Now this third one is having x prime prime. It's going to have x prime prime with an epsilon. Done. And then we take this one. This one, there's nothing there, so we just write it as it is. X prime x to the power -1, and x prime epsilon. Now, at this stage, there is something we can do. Watch it. If you take this one here, this x prime and this x, okay, I'm merging these two. Okay. When you pick them, you're going to have x prime x. It doesn't matter which one comes first, which one comes second. Oh. So it means that we are going to have x prime x for that one. And already this one there is x prime x to the power -1. Now remember, this one has no -1. So they'll go. They'll cancel because one has +1. We don't write it. One has -1. So +1, -1 will give you 0. Any number raised to the power 0 is 1. So that's gone. Now we are left with this one in the middle here, x prime x to the power -1, which is this one in the middle here. And now you have your error, the two errors. Remember, these two errors, one is a prime, one is not a prime. How do we know? Watch it. This error here has a prime. This error here has a prime. But the other one here has no prime. So that is the final thing here. At this stage, remember, we are taking the expected values of all of that. So if we take the expected value of all of these, what happens? It means that, I'm writing it at the top here. It means that we are going to have the expected value of x prime x to the power -1, and then the expected value of epsilon prime epsilon. Now, already the expected value of this one here is always going to be x prime x to the power -1. It doesn't change because it's a matrix. But the expected value of this is beautiful. You invoke an assumption known as homoscedasticity. Therefore, let me just jump all of this so that the thing doesn't become like Hebrew again. Everything is here. Okay. So eventually, when you take that x prime expected value of epsilon epsilon, it is homoscedasticity assumption, which is one of the assumptions of econometrics. And again, you're going to check the assumptions that we went through the last time. This was there. Therefore, our x prime x, what is the expected value of the epsilon square? That is an identity matrix, which is sigma square. And that is the assumption of homoscedasticity. Therefore, the variance of beta cap is a homoscedastic assumption multiplied by the x prime x to the power n. We have been able to prove, quod error demonstratum, that the variance of beta cap is equal to this. This, ladies and gentlemen, is a variance covariance matrix. Somebody is saying, what is all this mumbo jumbo? What is this whole Hebrew and Aramaic? Well, this variance covariance matrix is what we normally use to find the coefficient of the regression model. It doesn't only give you the beta parameters, or doesn't give you the variances, but also gives you the covariances. The variances are all in the right diagonals, and the covariances are outside of the right diagonals. But what do you need these covariances and variances for? Well, this is what we know. We know that the mean is beta. The expected value of beta is beta cap, and the variance of beta cap is beta. So the expected value of beta cap is beta. We know this already. And so beta cap is normally distributed with a beta and the variance covariance matrix. And the variance covariance matrix is the variance of beta. The diagonal elements I've told you are the variances. The off-diagonal matrices are the covariances. The variances are useful when you want to look at the spread in the data set. The covariances will tell you, which corresponding elements from the two sets, move in the same direction. The word covariances is a little bit of that we get even correlations. They help you to understand the various test scores. The test scores here are going to be the beta values and whether the beta values you found are statistically significant or not. What again are the usefulness of it? You can use them to find the standard errors. You can use them to find the p-values. In a logistic regression, the matrix can even be used for the estimated coefficient. It will tell you the variances of the coefficient, the covariances, and all of that. In other words, this whole mumbo jumbo are very necessary for you to interpret your results. The only thing is that the software will do them easily for you, and because of that, you don't even think that is happening, but it is happening. The only thing is that the software is doing it for you. The last time you looked at the dummy variable, so I'm not going to look much into the dummy variable. Now we are going to go into the application of the work. So please get ready. Get your R ready. Open your R and your R Studio if you have not already done so. We are going to write a thesis. We are going to write a journal paper. And the title of the journal paper is this. Now, guys, whenever you're starting a paper or a thesis or anything, by the way, a PhD thesis is like 3 papers. So when you're starting a paper, you conjure a title. And the title is obtained from your research in the literature. Whether you're using a Scholar Google, Rabbit Google, any of the search bibliographies. You search and search in the area. Your area will originally be broad, and then you got to now bring it down to a specific topic. So you would have created a tabular taxonomy, which is made up of names and other papers. A table which is a collation of all the papers that have been done in the area you are looking at, so that you are clear about who has done what, at what point in time, what is the connection between what are the theses, the antitheses, and the synthesis. You're able to get it all. Then you can now come out with your topic, of course, to be refined later. And so we have come out with a topic which is known as the determinants in the alcoholic beverage industry in Ghana. Now, whilst we believe that a lot of people have looked at the determinants of alcoholic beverages in the world and in Ghana and other places, the thing is that they have not looked at the impact of location. For those that have looked at the impact of occupation, they have not looked at trading, fishing, and other kinds of occupation. For those that have looked at the impact of religion, they've only looked at the impact of Christian religion. They've not looked at the impact of Muslims, okay, or the impact of being a Buddhist. So these are the gaps. Those are the problem statements. And now that you've gotten it clear, you have to now structure your introduction, your literature, your method, your results, your discussion and conclusion and references. Now, before we get down there, we have collected the data set. And I want us to go back to the data set, look at the data set, so that you can appreciate the data at hand. So this is a data set. Please, if you can see it, just type Y for me. So this is the data set that you have collected. You collected the data set from 40 shops, random sample shops. Do you see the data set? Okay. Now the first column of the data set is the quantity demanded of gin bitters. That's the first column. The second is that the quantity demanded of gin bitters, which is a dependent variable, this is actually influenced by the price of gin bitters, which is a P, the complement price of gin bitters, which is a C, the average income of the people, which is a M. Because the average income of the people will determine whether they will purchase the alcoholic gin. And it also depends on some categorical variables, dummy variables, location, occupation, and then religion. Now we can write these things in English because these are dummies. R loves it, but Excel cannot handle this. So we're going to take this thing to the R, and then we can make sense of this. How do you do that? You click inside, you highlight, and then you do Control C to copy. Then you go to your R Studio. Let's go to the R Studio. This is the R Studio. If I remember that you can generate the descriptive statistics, which I know you've done, the descriptive statistics, the correlation, and the entire regression in Excel, using the coded version, not using the English versions, not using the letter versions. So using the coded. So we come here, and then we can run a regression. But before then, we're going to do some quick things. Very, very quick, because we're going to do some descriptive statistics. That will help in you getting the picture. So this is the data set. Let me run the data. And again, you have all the commands. So this is the data set. It is showing here. In order to prove that the data is showing, I do that, and you can see the data nicely here. The data is beautifully showing in the console. Now, next thing. Next thing you want to do is, see, you have your entire data set. Of course, if the data was a lot, I will truncate it so you will not see everything. We can find a bit of information about it. Okay, there are so many things we could find about it. For example, we can generate a table that shows the number of, variables as against how many variables. So you can generate this table. Okay. In this command that I'm showing you, you can generate this table. This table will give you, among the rural folks, how many of them were fishers, teachers, and traders. I just created a contingency table here. So among those that are rural, okay, four of them were fishers. They were doing fishing. And out of them, and among the rurals, 4 of them were also doing teaching as their occupation. But then those that are doing trading are 12. 12. So traders are 12, and I'm looking at 4 plus 8. Teachers are 4, fishers are 4, making a total of 20. That is 20 people in the rural section. What about in the urban? In the urban, 12 of them were doing fishing. 8 of them were doing teaching. None of them was doing trading. So a contingency table gives you a feel of the distribution of the categories in the data set. And of course, you can also look at them according to Buddhist, according to religion. So you can see that the rural folks, 8 of them were Buddhist, but then the urban folks, 4 of them were Buddhist. The rural folks, okay, none of them were Christians in the rural sector, but all the Christians were in the urban sector, 12 of them. Okay, so there's a little bit of distribution of the data. Of course, you can draw a histogram of quantity demanded. How the quantity demanded is distributed. This is a histogram of that. You can do that. And again, you check the slides, you can be able to do all of that. You can create a lot of things, I'm telling you. And this distribution is using histogram, but it's not the best way to do distribution. So you can do other distribution. You can do distribution of the rural folks, how it's distributed across gene betas. Okay. You can plot the gene, just a scatter plot of the gene betas, how it looks like. You can plot the density of the gene betas, and give it some color. This is a density of the gene betas. Remember, gene betas is a numerical variable, and you can always plot the distribution of a numerical variable. Even numerical variable across groups, you can plot their distributions. And this is just a typical. This tells you that it has 2 peaks. It's not normally distributed. It is multimodal in this context. And it is spread, between 120, 150, and 200. You can test whether that variable is normally distributed. You can test whether gene betas Q is normally distributed. The quantity of gene betas is not, by using the Shapiro test. And again, it tells you clearly here. Okay. And when the p-value is this, it means that it's not normally distributed. You can look at several other things. There are several distributional analysis you can do, okay, that you can take a look at in this context. I'm going to jump away from that. Of course, you can do hypothesis testing of some of the variables across. We've done these things already, so I'm not going to go deep into that. The most important thing that I want to hammer on now, of course, you can also do box plot. You can do a box plot of gene betas, you know, to see how it looks like. This is a box plot of the gene betas between the rural and the urban. So you have two boxes. The black line is showing the median, and then you have the 75th percentile, the 25th percentile. You have the whiskers, and then you can determine whether or not there is an outlier. Nice. You've done all of this. Okay. Richard is talking plenty, you know, knowing very well we are in a class. All right, so let's move on. The next thing you can do, and again, these are not the main thing I want to do, that's why. Because religion is 3, okay, you can generate ANOVA of the religion. So this is an ANOVA of the religion. And you can check the p-value of the ANOVA here, and you will see that it shows that there is a statistically significant difference, you know, in the quantity demanded across religious groups. Quantity demanded of gene betas differ significantly across religious groups using the independent ANOVA test, which is what I just used here. Of course, if the data is normally not, if the data is not normally distributed, if it is skewed, then you don't have to use the independent ANOVA. You got to use the Kruskal-Wallis test for independent sample. Now I can run that, which means I'm assuming that, and again, it shows that there's a significant difference. Of course, anytime the p-value is 0 or less than 5%, it means that it's significant. I'm assuming if the data is independent, then that's great, like what I'm doing. If the data is dependent, then you use a Friedman. So you got to check your data. And again, you will see that. What I'm interested in now is to show you how you can use the R to generate the correlation. Remember, we've already said that the difference between correlation and regression is that correlation establishes relationship, regression establishes causality. But note that you can also find some few things about the data. You can check how many observations are in the data by using this command called string gen. So when you do that, you'll be able to check the data frame is made up of 40 observations and 7 variables. So it gives you a feel of the data. And then it also gives you, you know, the location. It tells you the content, what is made up of the location, the occupation, what is made up of it, a summary of it. You can use this one to also tell you whether there are missing values. Okay, so are there any missing values? And this one, the answer is telling you down here that there are no missing values. You can look at the total number of missing values, and here they are 0. There are no total number of it. You can ask a question: is there any missing value? And it tells you false, 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 false. Okay, which means that there are no missing values. So there are no missing values. And then you can even find the percentage of missing values. How many of the variables are, oh, for each variable, there are 0% of missing values here. You can do all of that. Again, remember, I'm coming to correlation. Okay, that's what I'm interested in. And all of this, you don't have to fully understand. When you take your time, you sit down, you can get all of them. Okay? That is the most important thing. Now, let's get lovely and move. We can generate a descriptive statistics of the data. I've said that multiple times before. By clicking this command like this, describe gene, it can give you a description. Now, it didn't work because you've not invoked require site. So once you do invoke require site, and you can now come and do describe gene, you can get it here. So as you can see, we have a descriptive statistics for the data. The fact that these variables have got a star indicates that they are categorical variables, which means that you don't need to focus on their descriptive statistics. You can even do a descriptive statistics across religion and across location. You can do across religion, across occupation, across location by using this command, describe gen. Describe gen. This describe gen according to religion. That's what you see here, according to REL, religion. When I do that, watch it. It will give me a descriptive statistics across the religious group. So you can see that among the Buddhists, okay, look at the Buddhist here. The N shows that the N, which is the first part here, shows that the Buddhists are only 12 shops in the Buddhist section. Christians, 12 as well. Muslims, the N column shows they are 16. And for each one, you'll be able to get the descriptive statistics. So how many of the Buddhists are having, what is the average quantity of gin by the Buddhists? 180. What is the average price of a gin among the Buddhists? That is 15.17. You'll be able to get a feel of all of this. Again, remember, this is not really my focus of today, but I'm just summarizing some few things for you. You can also do a graph and put all the graphs in, in one page, okay, using the PA-info method. I will not show that, but you can always look at it. Okay, they are in the slides. Okay, now let's go to the correlation. The correlation, because these variables are actually numerical, categorical and numerical, we cannot do the correlation on the coded. We are going to use the correlation on the categorical. So that means that we have to remove these ones. Watch it. I'm highlighting them. We have to remove these ones, the location, the occupation, and then the religion. And the command to remove that is by using call gen, okay, square bracket, comma, in which these ones must be removed. And once you do that, you can now get a correlation. I'm going to do that for you to see. So this is a command I'm running. And once you do that, you see, it is giving you the correlation matrix for only the numerical variables because you have removed the categorical variable. Why? It won't work because first of all, the categorical variables you are dealing with, you want to find the correlation between categorical variables. You see, these variables are not changing. Categorical variables are dummies. They are fixed. They are stagnant. They are categorical. They are static. Static. Static stands for statue. Statue. Stagnant. They are not changing. So if a person's religion is Buddhism, every year he will not be changing their religion. If a person's religion, on average, we are speaking on average. If a person's gender is say male, every year is unlikely that that person will be changing the gender. No. So, and again, we are talking about on average yearly. But then when you look at price will be changing multiple times in a year. And every year it will be changing. So those variables are continuous variables. They are not static. They are not categorical. They are numerical. And so we only look at the correlation on the numerical variables, and not just on the categorical. Oh, that's beautiful. Or not just on the categorical data. Hey, I should drink some tea this morning. Then we can generate the pairs, the correlation pairs as well. So this command will give you the scatter plot. It's a graph. This one is a graph of the same thing you see here, but these are numerical tables. This is a table with numbers. We're going to show the same thing, which is a graph. Okay. Let's run that and then you see. That's it. You can look at it here, and you can see that it's a graph that shows you. So if, for example, I want to tell, if I ask you that tell me the relationship between Q and C, is it positive or negative? What would you say? Who can raise a hand and tell me? Or who can just tell me the answer? The correlation between Q and then C. What is the relationship between Q and C? Who can tell me? Just using the scatter plot matrix. This is a scatter plot matrix. What would you say is the relationship between Q and C?
Hello, Prof. Can I?
Yeah, go ahead.
Yes, I think it's positive because if you see the scatter plot, the in the box at the edges by connecting the two sides. They seem the same. The one up there.
This and that is positive. And it's the same way when you go this way. Oh, sorry, I've jumped it. When you go this way and get here and this way, it's the same graph there. Okay. And that is true. It shows clearly that it is positive. And that graph will give you a clue. So when you come to the table, okay, when you come to the table here, between Q and C, this is it. This is the value. And again, you can see that the value here is positive. And again, when you go to the other side, between what do you call it? C and Q, this is the same value. It's positive. So the numbers will tell you again what the letters are also telling. So this is a way of showing the relationship numerically and graphically. Next one. The next thing you can do is that you can generate the whole table with correct to a certain decimal. So if you look at this command, 200 here, there is a decimal number I have placed after the entire bracket. I've placed a decimal number 2. So I'm indicating that I want you to generate the correlation matrix, the table, but correct to 2 decimals. You see, the one I have down here, the decimals are many. So I can just run this one, then it gives you only up to 2 decimals. Oops. This is it. I think I switched some things. Okay. So if you look at that, you can see clearly that the correlation that you are getting here is now in 2 decimals. So you now have 0.72, you know, which is here. Remember, all the diagonal values are always 1, 1, 1. So the beauty of this is that you're able to get a correlation in 2 decimals. Okay, let's move on. The next thing we can do is to now do our regression. We can do a simple regression, and we can do a multiple regression. Now, if you go and run this regression without attaching the data, and again, we've spoken about attaching and detaching, okay? It might not work. Sometimes it might work, but I have attached it already, so that's why it's working. So you need to run attach, and don't forget to detach later. And then you run this 227 command. This 227 command shows that quantity demanded depends on price. We want the color of the quantity demanded, the data point, to be blue. And we want the line weight to be 2, which means that it's a bit thick enough. The name of the data is the gene data, and we want to give it a title called scatter plot of X and P with a fitted line as a plot. Then we go to the line. The line we use abline. Now, this is usually possible only after you've run the simple regression, which is in the next row I'm about to do. So the abline is the same name of the simple regression. The line weight this time is 4. The color is red. And so you can see all of that shown here. And we have a beautiful graph showing a regression there. What does this regression tell you between quantity demanded and price? It tells you that the relationship is what? You can tell us. And why do you say so? What is the relationship between quantity demanded and price? Just looking at the graph. You see, so in some of your assignments, I will ask you that determine whether there is a relationship between quantity demanded and price graphically, only graphically. I'll ask you, and I will expect you to do all the graphing, name it, and all of that. Okay. So when you look at a relationship, is what? Negative. Okay. Because you can see that as the price is increasing, the quantity demanded is falling. Okay. So that shows a negative relationship between price and quantity demanded. It has a fitted line. We've explained all of this theoretically. This is on our real data. Remember, we collected data and we are fitting the data. Now, the 229 here is the linear model regression. I decided to call it gene simple. That is a simple regression. It's a linear model where quantity demanded depends on price. The summary will give you the entire result. So I'm going to do that and look down here in the console, you get a result. Boom. This is a beautiful result. The thing about the result is that the result will also give you the linear model as it is here. It will give you the residuals. Most of the time you don't need it. But what you need the most are the coefficients. And then the rest of this information. This is what you need. Beautiful. What is that? It gives you the estimate, the standard error, the t-value, and then the p-value. Remember, this thing is called the p-value. The p-value. The p-value. What is that? Well, before I tell you everything, just let's make some sense here. And again, you should ask questions if you don't understand. Because when you understand, that is when I know you are silent, because you get it all. What you want to do is to always note what the estimates mean. You should know that. You should know it so well. The estimates are the same as the coefficients. They tell you by how much each independent variable affects the dependent variable. However, because this is just a simple regression, we have only one independent variable, which is price. Please remember that the intercept is not price. The intercept is never an independent variable. The intercept is for cosmetic purposes. It's not useful except during prediction. And you should read about it because I've set some questions on that. It's only useful during prediction. Note it down. So in this case, because the regression independent variable is just one, price, that is why you can see it here. So who can tell me what is the coefficient of price on quantity demanded? What is the coefficient of price on quantity demanded? Yeah, you can tell us. What is the coefficient of price on quantity demanded? I'm giving you this, but they're all in the slides, by the way. Negative 14.26. What does this mean? And because price is a numerical value, numerical variable, it's not a categorical variable, it's not a dummy. Okay, you will interpret it as if it's rising or falling. But if it was a numerical, categorical variable, you will not interpret it like that because they don't rise and fall. Religion doesn't rise and fall. Location doesn't rise and fall. Occupation doesn't rise and fall. But price rises and fall. Income rises and fall. Complement price rises and fall. Okay. We'll come to this when we come to the multiple regression, but I've just given you the idea. So what does this mean? It tells you that on average, given the complement price, okay, the income of the people, the location of the shop, the occupation and religion of the people, the 1 unit increase in the price of gin will reduce the quantity demanded of gin bitters by 14.26 units. That's what it means. So sometimes we are tempted to say that holding all other factors constant when we don't even know what those other factors are. That's why I decided to mention those other factors for you. So this is how you interpret. So what it means is that, ceteris paribus, what it means is that if you should raise the price by 1 unit, and I don't want to use dollar, I don't want to use dollar, CD, pound, anything. I'm just using units to keep it simple. If you raise the price by just a unit, quantity demanded will fall by 14.26 units, which is okay. But the question is whether it is significant. Is that significant enough to say that price solely and really influences quantity in this data? Is that significant enough? Who can tell me? Is that significant enough? Who can tell me? I know I'm not touchy, but who can tell me whether that's significant or not? And what is making you think it's significant? Do you think that is significant? Is that significant? That quantity demanded is influenced by price? Or it's not significant? Is that warranted? Is that powerful enough? And in this context, yes, go ahead.
I'm trying. Yes, it's significant because the p-value it's less than 0.05.
Perfect. Excellent. I always have someone who is walking with me on the desert sea. The person is walking with me in the desert and riding with me on the sea, in the middle of the thick blue sea and the devil. There will always be the 80-20 rule. So if you look at the p-value, because the p-value is almost zero, it means that the price is significant. The fact that it is 3%, I mean 3 stars, means that it's significant at 0.1%. That's what I mean. If it is significant at 0.1%, which it is in this case, it also, and that is for this one, by the way, 0.1%. If it is significant at 0.1%, it means that it's also significant at 1%, and it means that it's significant at 5%, and it means that it's significant at 10%. So, in fact, the lower the p-value, the lower the significance level, the best. If the stars are 2, it means that it's significant at 1%. That's this. If the star is 1, that means it's significant at 5%, which is this. If there is a dot, it means that it is only significant at 10%. And if there is nothing at all, no star, no dot, nothing, it means it is insignificant. It's not significant. So when we come to the multiple regression, all of this will make sense. Okay. At this stage, I want to share something with you when it comes to the residuals. Now watch this gap here. I want you to check something. See, the beauty of this word is your ability to follow these things. So when you look at this, there's a gap between this data point and then the regression line. There's a gap between this data point and the regression line. There's a gap between this data point and the regression line. There's a gap. 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 Okay. And all of these gaps are called errors. Some of them are positive above, some of them are negative below. The essence of regression is the expected value of the error term should be 0. We've learned this multiple times. So if the expected value of the error is supposed to be 0, we need to check whether watch the word. The word is, I just want to go here. So the word is the expected value of the error term is 0. That's what it says. The expected value of the error term is 0. So my question to you is this. The expected value of the epsilon is equal to 0. The word expected value means the mean. The mean of the error is 0. That's what it means. So we want to check whether the mean of the error is 0. Now, how do you find the mean of the error? Well, watch this. Y is equal to x beta plus 0. This is the I formulation. If I want the error is actually going to be the y cap estimated. Okay, so that is a y cap minus the x beta cap. The y cap minus the x beta cap. So the question is that, what is the y cap? This y cap is a predicted y. This is a predicted y. And what about this line here? What is that? That's the actual. Okay, so this one is the actual. So the error is the predicted minus the actual, which means that the predicted will be the actual minus the error. Or the, what do you call it? Yes, plus the error, the actual plus the error. So we are going to use that principle here. So when you come up here, I'm going to create you the fitted, okay, which is a predicted. This command here, 231, is going to give you the fitted. The fitted are the ones that it should have been. So each observation, remember there are 40 observations. Each one has its actual value, and then it has its predicted or fitted value. Let me show you. Look at it. So look at value number 1. This is observation number 1. And I want you to pay attention because this is a beautiful knowledge you need to teach somebody one day. Don't say that I will never need it. You will need it. You will need, in fact, you already need it now. So when you look at this value here, let me just get a very nice, this one, okay. If you take that variable and you check this variable, the value you are seeing here is 162.16. Okay, 162.16. Do you know that the Excel version of that value? Okay. Because when you know the Excel version, let me show you the Excel version. But let me see whether I can share my screen. Okay, I'm sure you can see. So let's go to the Excel. This is the Excel. Please confirm if you can see the Excel. So this is the Excel. And observation number 1, the value is this. The value is 160. Okay, that's the value, 160 here. Now the question is that this was the actual Q, 160. What is the predicted Q? The predicted Q is what you are seeing here. The predicted Q is 162. So what this means is that the actual value deviates from the predicted value. And that deviation is an error. The actual value deviates from the predicted, and that deviation is an error. And so you will see that the error is going to be the 162.16 here minus the 160. But remember, it is actually the actual, it is the actual minus the predicted. Is it actual minus predicted? Let me see. Okay, I've cleaned the other ones. So yeah, the actual value minus the predicted value. That will give you the error. So how do we find the error? Let's find the error. Remember, the error is this. I'm putting it here for you to see. So the error is the actual Q minus the predicted Q. Okay. Now, what you are seeing here is the predicted Q. This is the predicted Q. Where is the actual Q? The actual Q is the one in the Excel. So the actual Q, which is a 160, so it's going to be the 160 minus a predicted 162.16. And so we are expecting the error to be negative 2, blah, 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 blah. Let's run that in R and see. So when you go to this command here, 282 command, this is the error. And look at it. Okay. Look at it here. What value is this? The value is the value you see. That is the value. Okay. So you can see clearly from here that the value is exactly negative 2.16, which means this is the error for this observation. When you go and check the other one, this is the error for it. The other one, this is the error for it. The other one, this is the error for it. The rule of regression says that when we take the average of these errors, the expected value of all of these errors, we should get what? Who can shout in the answer? We should get what? And take the average of these errors. What should we get? What value should we get when we take the average? Beatrice, Edmond, or they are not able to unmute themselves. Let me see. Yeah, they can.
Hello, Prof. Can I try?
Okay. It doesn't mean that they are not online. They are not with us at all. Is that what they are saying? Okay. Laura, go ahead.
I want to assume that will be the standard deviation.
Now, when you take the average of all the numbers, according to the assumptions of regression, the expected value of these errors put together is what value? Is 0. Is 0. Okay.
Zero still.
Don't
Zero.
worry. I mean, you are here to comment, and you are all sitting down watching me. That's beautiful. Let's move on. So the mean of the residual is 0. So you get 2, 3, 3. So I'm going to run this mean, and this is what I had, which is negative 4.4, blah, 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 to the power e minus 1. And that value is exactly 0. So this means that expected value of the error term is actually 0. You can also find the confidence interval. You can run this command, and it will give you the confidence interval for each. Because we're having only one independent variable, the confidence interval is that. Remember that the regression actually told us that the coefficient for the price is negative 14. Okay, and you can see that negative 14 is truly between negative 16 and then negative 11. Okay. So clearly, you have all of those necessary information right there. Okay, and then of course you can find the ANOVA version of it. And again, the ANOVA will tell you that the p-value is 0, which means that all the coefficients jointly significantly affect the quantity demand. In this case, the coefficients are just 1. It's just 1, which is price. But when we come to the multiple regression, I will take my time and explain each one of these variables right there. Now, let's look at some few things we can do with regression before we go into the nitty-gritties. One, this that we did is just one dependent variable, one independent variable. But you can do other kinds of regression. You can do multiple regression. I just want to do 2 variable case, not 1 variable case we've done. To do that, we'll run this command called library rgl and library car. You install these 2 packages. And then after installing and running this package, we can do a regression. So this is a regression I want to do. Okay. I want to do a very, very interesting regression, which I will call 3 variable case. I want to look at the quantity demanded. Okay. I want to look at quantity demanded, how it is affected, influenced by price and then complement price. So I've just made the independent variables 2. I'll add the rest, but I just want to do 2. And then we see how the graph looks like. Of course, because the independent variables are 2, you can never get a line. You rather get a surface, a polyhedral surface. So let's run the scatter plot and see how it looks like. It looks quite strange, okay. But it's also beautiful. It's also beautiful. It's also nice. So this is it. Okay. It's come up here, and you can see how it looks like. So look down here. At the down here, you will see C is there. At the right here, let me click and drag. You can click and drag and then to be moving. Okay. At the right here, you can see the price, and at the top, you can see the quantity. That thing, if I start moving the thing this way, you see that it's becoming a line. It's becoming a line. It's becoming a line for 2 variable case. For 2 variable case. And boom. This is just between quantity and price. That's it. It's a line. It's a line. It's a line. Okay, because I'm just dealing with quantity and price. And you can see that the filter line is there. And you can see that the lines, this is beautiful. The observation above, they create a positive error. So the distance is green, sort of. And then the observation below the line, they create a negative error. So the distance is marked as kind of pink or red. And then the observations on the line, they don't have anything because they are fitted. Okay. Now, when you now add the second variable, now let's drag it. The thing becomes a surface. Okay, it becomes a surface now. It becomes a surface. And then the surface will just be working in that way. So it's just a beautiful way to know that once you move away from simple regression, start going to multiple regression, everything becomes what? Becomes a surface, a polyhedral, a polygonal situation, no longer a 2x2 Cartesian plane, but it becomes multiple. So this is a multiple regression, 2 variable case. Okay. There's another graph you can use, okay, which you can use to run the multiple regression. This one is like this. So you can see that this one is similar to the previous one, but it doesn't move. That's a beautiful thing. It doesn't move. Okay. But you can see that again, it has C there, it has Q there, it has P there. And the variables are all shown inside. So we now have a kind of a cuboid or a polyhedra in the process. This is to let you know that there's a way to draw 2 variable case, 4 variable case, 3 variable case. At that stage, you are now going to higher level hyperplanes. Okay, now we are done with simple regression. We are ready for multiple regression, multiple regression, multiple regression, multiple regression. And so I'm going to now show you how to do the estimation of the multiple regression. Simple, it's just the same thing as a simple regression. You load the data, and this is a command for the multiple regression. I called it gene multi. You can call it OPELE. You can call it anything. I call it gene multi, and LM here shows that it's a linear model. It's a linear model. Q is a dependent variable, and this sign is a tilde sign. It is on your cursor, on your keyboard. So Q, and every name you're writing should match up with what is in the Excel. So when I go to the data set like this, okay, and look at the data set, look at the headings. The headings are Q, P, C, M, loc, OC, REL. So the same name is what you're going to use to write the command. So when you go to the command, the Q is dependent on P, C, M, L, O, C, O, C, C, REL. And then the name of the data is gene. Then you add semicolon summary of the name you give to the multiple regression, which is gene multi. Remember, this is real life. This is thesis. This is beautiful thesis. This is a paper submitted to a reputable journal. And so you run this and watch what's happening. Oh, this is beautiful. It shows you the beautiful result you will ever see in any regression analysis. Of course, it's not a regression analysis. Okay. The most important thing is that the name of the command, the running command is here. So you get everything. This is the formula. And as I told you, the residuals information are here, but those are all not important. What is important is starting from the coefficient. From here is a regression. This, ladies and gentlemen, is the most important aspect of the regression that you want to go on. So if you check, everything that I've done is in the slides here. This is what I just did. And there are some few other things you can do after you've generated a regression. Let's go here. If I were you, when I go home, I'll take my time and run all of this in my R myself, whilst I have the video on the side. After you run the multiple regression, I'll come and interpret it. Don't worry, we'll come and interpret in total everything here. Because it's interpretation that matters, it's not just the estimations. After this, you can also estimate the confidence interval. Why do you need a confidence interval? Well, some people are very, very complex. They love complexities, and sometimes they want to use a confidence interval to make a speech. And so you can estimate a confidence interval by using this command. We will estimate it correct to 2 decimal places. So we'll start with a round confidence interval of the gene multi, correct to 2 decimal places. And this will give you the confidence interval using the profiled log likelihood estimation. Don't worry about these words. And for each variable, each independent variable plus the intercept, you will get the confidence interval, for the two-tail. Okay, for the two-tail. You get an upper bound and then the lower bound of the confidence interval. And so the lower bound first. So for example, for price, the lower bound is this, -6. The upper bound is that. So that means that in the actual work, it should fall in between. If it doesn't fall in between, it's not significant. So we go up here, and you can see that the price, the estimate or the coefficient is -3.15. So we come back here, -3.15 is actually within the confidence interval, -6 and 4.04, which means that it is within and hence is significant. But we'll come back to that. You can even estimate some beautiful other things necessary for regression. You can find the mean of the residuals. If you want to measure the accuracy of the model, you can. You see, there's something we use to measure the accuracy of the model. We'll come back to that. It's known as the R-square. The R-square. But you can also use the mean of the residuals to measure mean squared error. Okay, this is it. You can use that to measure this. And then the square of the mean residual. This one. We'll come back to all of these and how to make sense and interpret them. I just want to show you how you estimate them. You can estimate the ANOVA of the data. And this will give you the ANOVA of the data. It's fairly simple. If you've done ANOVA before, this is simple. You can again find the fitted for the predicted. You know, I'm talking about the kill, the actual fitted. And this is it for each variable. You can see that now the gaps are smaller because we are dealing with multiple regression. Before, the first observation was 162, now it's 161. So the error will be smaller here. And then it goes on and on. Let's check the residuals. And these are the residuals for each one. Remember the first one, the residuals was just -2. This one, it is -1. So it gives it. Now we can find the mean of the residual, the expected value of the error. And again, you can see that it is 0. Now, if I ask you this one and the previous one, which one is more 0? This one is more 0 than that one. Okay, look at the last number. Okay. And then go to the previous one that we did, and let's check the last number there. What I'm showing you, it's not everybody who spot it. So when you go to the previous one, look at it. Look at the last number. Okay. So that shows you clearly that the multiple regression has got, the errors are very, very zero than the simple. Okay, you can also plot the residuals. You can plot the residuals. We'll look at them later. Okay, you can plot the residuals. You can plot. You can do a lot of other estimations. But for now, we want to interpret the results. So let's go back to our data. This is it. This is our result. And I want us to interpret the result. I want us to interpret the result. So how do you interpret this? There are a couple of questions you should know here. Question number 1. Oh, by the way, any questions so far? These residuals points are here. Hold on, let me see. Okay. So there are a few things I need to do before I come to the interpretation of the result. And they are the residuals, but I will jump them, I'll put them because they are all part of the regression diagnostics. So I'll look at all of them next time. Then we can focus on the interpretation of the residuals. So what I'm going to do is I'm going to just jump these and then we'll go straight to the interpretation of the residuals. And even the other beautiful aspect of the tables, because these tables are nice when you're dealing with proper work. The star design, all of that. Okay, so let's go to the first question. And again, you want to note it down. Let me first show you the data set. There are other tables you can present, but this is a data result. Okay. I'm going to show you in the Excel, in the R. So let's go down to the R. I'm going to print. I'm going to go back to the results. This is it. Because my focus is you making sense of everything here. And then we can make beautiful, beautiful move of everything. Okay, so look at this result. This is the most important result. And I want you to answer the first question for me. And the question is, what's the question? Let me see. So the first set of questions that is seen. Which variables are significant, statistically speaking, and which variables are not significant? So who can tell me which of the independent variables are significant and which of them are not significant? Who can tell me? And then, of course, you give me your reason. Should we take a break? Should we take a break?
We can continue.
Okay. We've got 30 minutes. Okay, good. So the first question is to tell which variables are significant and which variables are not significant. Now note that a variable is said to be significant if the p-value is 5% or less. A variable
So the
is said to be significant if the p-value is 5% or less. Sometimes some people put that number 5% to a different number, so different. But it's not just saying whether the variable is significant, but also significant at what percent. So let's take the variable price. The p-value is correct to 2 decimal places is 5%. So it means that price is significant. What do we mean by price is significant? First of all, price is significant at what percent? Who can tell me? Price is significant at what percent? Price is significant at what percent?
Let me try. I think 1 point. Oh, sorry.
Price is significant at what percent? Okay, if you look at the dot, it shows that price is significant at 10%. Price is significant. When the value is a dot, it means the variable is significant at 10%, which is this one here. When the value is 1 star, it means the variable is significant at 5%. When the value is 2 stars, it means the variable is significant at 1%. When then it is 3 star, it means that it's significant at 0.5%. That is how you got to attack it. So as a form of repetition, I'm saying that when you check a particular independent variable, like this one here, and after checking the independent variable, you realize that that particular variable has got a star, a dot like this. The dot means that it is significant at 10%, which is reflecting here. You see, at the bottom here are the interpretations. If it is 1 star, now in this case, there's no 1 star, it means that it is significant at 5%. If it is 2 stars, it is significant at 1%. And if it is 1 star, if it is 3 star, it is significant at 0.1%. So we have 10%. That's the first one we have. We have, let me write it here, then I'll go. Okay, we have 10%, we have 5%, we have 1%, and then we have 0.1%. So that is what it is. If there's any particular independent variable, if you want to know, you check. But another thing you do, okay, which you will be asked, is that it's not all the time in that format. You should also look at the p-value. So when you look at the price, the p-value is correct to 2 decimal place. It is exactly at 5. And therefore, it is significant. Okay, it is significant. But ideally, the software is telling you that it's significant at 10%. Why? Because it is taking all the other decimals. So that is 5.3%, which is more than 5%. So if it's more than 5%, it means it's significant at 10%. Let's take the second one here. Okay, and let's not even round them up. If you look at the second one, when you check the value carefully, you see again, when you check this one, you see that it's not 3%, it's 2%. And from what we have indicated, sorry, it's not 3 stars, it's 2 stars. As you can see, it's 2 stars here. So that means that it's significant at what percent?
1%.
1%. 1%.
It's significant at 1%, exactly. And when you come and check the values, it will give you a clue, because when you look at the values, you can see that it's not 0. Even when you round it to 2 decimal places, it is exactly 1%. So that shows that it's significant at 1%. But it shows it's significant. But when you check this one here, what will you say about the significance? You can tell us. What will you say about the significance? Significant at what percent? Is it significant?
No, it's not.
Yes,
It's not.
it is.
It is not significant.
It's not
First of all, if it was significant, you would have seen a dot, a star, 2 stars, 3 stars.
20%. Yes, so it's not significant.
That is one way. The other way is that you should check the p-value. If the p-value is less than 5%, then it is significant.
Okay. Okay.
And here the p-value is 20%. 20%, which means that it's not significant at all. The next one, the p-value is 19%. It's not significant at all. That's why there's no dot, there's no star. What about occupation teaching? Is it significant or is not?
Significant.
At what percent?
Significant at 0.1%.
0.1%. Excellent. Excellent. It's significant at 0.1%. So, and of course, that's how it is for all the others. They are all significant because they are all 0, 0, 0, 0, 0, 0, 0. Now, so what we say if an independent variable is significant, what it means is that that variable has a higher much influence on the dependent variable, holding the other factors constant. So you should know which variables are significant, and you should always know which variables are not significant, using the variables themselves and also using the p-values. That is important. Now, let's look at the joints. So these are partial significance. Everything we've spoken about here is partial. Partial means individual significance. That means you're looking at each independent variable. Each. But let's look at joints. The joint question is that, are the independent variables jointly significant? That's the question. Are the independent variables jointly significant? That word jointly means together. An independent variable, for example, if you look at M is not significant. Influencing the quantity demanded. M is not significant. The location is also not significant. So location urban is not significant. But when you combine all of the variables together, are they significant? The only way you can tell that is use the p-value of the F statistic. That's what you use. Use the p-value of the F statistic. The p-value of the F statistic will tell you whether all the independent variables are jointly significant. All the independent variables are jointly significant. That is the p-value of the F statistic. So take note of that. And in this case, the p-value of the F statistic is almost 0. It's not almost, it's 0. And that means it's less than even 5%, 1%, 2%. All of them is less than even 0.1%. Therefore, we can say that all the independent variables are truly significant because the p-value of 2.2 e minus 16, that is the exponent, is less than 5% and significant at 0.1%. Therefore, all the independent variables are jointly significant. What is the difference between using this F statistic to determine the joint significance? And how is that different from the R squared? What is the R squared? What is the R squared? What is the R squared? We'll come back to that though. But for now, I want us to go to the next thing, which is interpreting the variable. So note the difference between partial significance and individual significance. Partial significance looks at how an individual on its own, independent of the other ones, how it significantly affects the dependent variable. Whereas the joint significance looks at how the independent variable together affect. All of them will use the p-values. The joint significance will use the p-values of the f-stars. Now, let's go to interpretation of the independent variable. So we are going to begin with price again. And you want to write some of these things down because you can use them. In my relationship with you, I'd never want you to be saying that holding all other factors constant, holding all other ceteris paribus. No, I want you to mention the factor because there's some learning in the process of mentioning the factors. So I'm going to interpret the price for you. Take note, document it, so that you can interpret the others as well. Price. How do you interpret price? What is the interpretation of the coefficient of price? First of all, look at the coefficient of price before you start your interpretation. Second, ask yourself whether that variable you are going to interpret is a numerical variable or is a categorical variable before you start. So tell me, is it numerical or categorical here?
Numerical.
It's numerical. Yeah.
So we know that numerical variable is a rise and fall. So how do you interpret price and its effect on quantity demanded of gen? This is how you started. You say that on average, because this is an average measurement, given the complement price of gen, so you mentioned the full name, and the complement price of gen is C, but you don't write C, you write English. Given the complement price of gen, average income of the people, given the complement price of gen, average income of the people, which is the M, location of the shop, occupation and religion of the people, occupation and religion of the people, a 1 unit increase in the price of gen, a 1 unit increase in the price of gen reduces the quantity demanded of gin bitters by 3.15 units. Correct to 2 decimal places. 3.15 units. And this is significant. And this is significant at the 10% alpha level. And this is significant at the 10% alpha level. And this is significant at the 10% alpha level. This is how you interpret the price. Watch it carefully. Watch it carefully. I indicated that whilst I was interpreting the price, I did not hold the price constant. I held the other factors constant. So I started by giving. The word giving means I'm holding them constant. So I held the other prices, the other factors constant. Complement, price, income, location, occupation, religion. I held all of them constant. But I was also very particular about the way I mentioned. I said location of the shop. And then I said occupation of the people. I didn't say location of the people. Because the shop is different from the people. So it's the location of the shop and the occupation. Is the lexis and structure. This that you have to make it work. Then I indicated that a 1 unit increase in the price of the independent variable, a 1 unit increase in the price of gin. So it is the price of gin you are increasing. So the negative 3.15 is not for the price, but it's rather the effect of the price. And so the negative 3.15 is on the quantity demanded of gin bitters. So I said a 1 unit increase, a 1 unit increase, the word unit must come. A 1 unit increase in the price of gin reduces the quantity demanded of gin bitters by 3.15 units. Why did I say reduces? You can tell us. Why did I say reduces?
Hello, sir. Please, because of the negative sign.
Exactly, because of the negative sign in front of the 3.15. So if it was a positive sign, you would say increases. So take note of that. And then after that, I ended with, and this whatever you said is significant at 10%. 10% because I was looking also at the dots here, which is for 10%. Very, very important. If I should ask you to interpret the coefficient of complement price instead of price, who can do that?
Doc,
Yes.
let me try.
Go ahead.
Average, given the price of gin, income, average income of the people, the location of the shop, occupation and religion of people, a 1 unit increase in price of complement will lead to a 0.114 in quantity demanded of gin bitters, and this is significant at the 1% alpha level.
That is wrong.
Say that is wrong.
So who can raise a hand and correct it? You see, it's easy to spot someone's mistake, but it's not easy to start yourself. But never correct a mistake in this world when you don't have a solution to the mistake you are correcting. Nazifa.
But I want to give it a try. So, yeah. So on average, given the complement price of gin average, with given the complement price of gin, which average income of the people, which is N.
Let's stop there.
Location of the shop, occupation of the people.
The reason why I say let's stop there is that initially, I think you were not prepared to do it, and then you had to raise your hand because you had corrected it. I think you should take your time and document it before you say it, because you started on a wrong foot. If you are interpreting complement price, you don't also say on average, giving complement price again. So who can come in, by the way, put your thoughts together. Who can come in and then give us, unless God, you want to just come back and then correct your. By the way, that is if you know why we made a mistake. You said 1%, but it was 5%. Oh, sorry. Hold on. It was still 1%.
That can write.
It was 1%. So what do you say? Say what you said again. Let me see.
Okay, Doc, let's go again. On the average, given the price of gin, the average income of people, the location of the shop, the occupation and religion of the people, a 1 unit increase in price of the complement will lead to a 0.114 in quantity demanded of gin bitters, and this is significant at 1% alpha level.
Okay. So that's fine. That's fine. The only thing is that I don't know why he kept saying 0.114.
I said 0.114 or reduction.
Fall. Okay.
Fall, yes.
Okay. Reduction. Exactly. Perfect. That's it. Okay. That's it. So that was originally the same thing you said, which was perfectly correct. So guys, you got to learn how to interpret this. Now let's go to the dummy variable interpretation. The dummy is static, so it's not like price, which is rising or falling. So I'm just going to interpret the coefficient of religion Muslim. Okay. Before you interpret any dummy, there are a couple of things you got to note. First, you got to ask yourself, what is the reference category for that dummy I'm interpreting? What is the reference category? Now, what do I mean by reference category? So we are interpreting religion Christian, religion Muslim. It means that you got to know the other levels of religion. Who can tell us all the levels of religion? Who can tell us all the levels of religion? Nazifa, it's your hand up. Otherwise, lower it. Who can tell us the levels of religion? Francisca.
Hello.
Go ahead, Francisca.
So the levels are 3.
There are 3 levels. You see, again, that's why
Yes,
I keep
please.
telling people, don't shout the answers in the air. Okay. You go and shout the answers and say 2. And now you are wrong. You say 8. So just raise your hand. When you raise your hand, your brain has restructured itself to be the correct one. So there are 3. Give me the 3, Francisca.
So the 3 you have Buddhist, you have Christian, and you have Muslims.
All right, okay. And from here, which one is a reference category? I'm not taught you, but which one do you think is a reference category from here?
Buddhist.
See those who shout answers into the air again. Which one is a reference category? Francisca, your hand is still up. You don't want to holler, so you put it down. Okay, so that is Buddhist. And because it's Buddhist, you got to keep that in mind when you're interpreting. The reference category is the one that is not always in the result. I will not bring the reference category in the results, so we should know. Okay, so let's start. How do you interpret it? We start with on average, given the price and complement price of gin. On average, given the price and complement price of gin, average income of the people, location of the shop, and occupation of the people. You see, I didn't talk about religion. And occupation of the people. Quantity demanded of gin bitters is predicted to be. Quantity demanded of gin bitters is predicted to be, or is expected to be. Quantity demanded of gin bitters is predicted to be 23.01 units. Quantity demanded of gin bitters is predicted to be 23.01 units less if the people are Muslims than Buddhists. Quantity demanded of gin bitters is predicted to be 23.01 units less if the people are Muslims than Buddhists. And this is significant at 0.1% level. And this is significant at the 0.1% alpha level. Fantastic. Who is not clear with that? Okay. Since you are.
Hello,
yeah.
Doc. Please, could you go over again for me?
All of it, you mean?
No, the interpretation.
Yeah, I mean, all of the interpretation, I just did all of it.
Oh, you just ran through just one and I'll be fine.
Okay. On average, given the price and complement price of gin, average income of the people, location of the shop, and occupation of the people, quantity demanded is predicted to be 23.01 units less if the people are Muslims than Buddhists. And this is significant at the 0.1% level. And this is significant at the 0.1% level.
Thank you very much.
So these interpretations are very important. In your assignment, in your exams, these things are very crucial when you are interpreting. They are significantly crucial whenever you are doing your interpretation. Okay, so who can do an interpretation of occupation teaching for us? Occupation teaching. I mean, God, you did some beautiful work, eh? You did some real beautiful work. So I want to see who can do the interpretation. Who is ready to challenge the orthodoxy? Interpret the coefficient of religion for the class. Remember, people that are hungry, they live a life of zero excuses. People that are hungry are unstoppable. People that are hungry are relentless. People that are hungry are forceful. People that are hungry are daring. People that are hungry are unstoppable. They do not complain. They do not make excuses. They chain on. They bend their ships. They tell them, I will go all in before I go all out. They know they are the head. They are never the tail. They know they are masters of their own work. They know they can do it. Even if others cannot. Even if no one can, they can. A hungry person does not need to be forced to eat because he's already hungry. If I were you, but I'm never you, I will always go through all the videos before I come. So go and learn how to do the interpretation of all the other categorical variables. It will shape your mental disposition. It will help you, and you will, by all means, be standing on your acre of diamonds. Ladies and gentlemen, that brings us to the end of the entire caboodle. What a day it has been. Remember to drink deep or taste not the Pyrenean spring. Their shallow drought will intoxicate your brain, and drinking largely will sober you again.